What if the universe grew up far faster than we ever believed was possible? A structure sitting 12.7 billion light years away has just been officially confirmed, and according to every timeline we trust, it should not exist yet. Before we go any further, smash that like button, hit subscribe, and send this to one friend who loves a good cosmic mystery. Trust me, what comes next is going to make you rethink a lot of what you thought you knew about the early universe. Now, let's start with the two telescopes that just made this entire discovery possible. Because without these specific tools, no one on Earth would ever have known this was real. The first telescope is the James Webb Space Telescope, often just called Webb. It launched in December of 2021 and now sits roughly 1.5 million kilometers from Earth, parked at a quiet gravitational spot known as the second Lagrange point. From there, it stares out into the darkness, but it does not see the same kind of light we see with our eyes. It is built to detect infrared light, which is the kind of light that comes from objects so far away that their light has been stretched out by the expansion of the universe itself. This stretching effect, known as redshift, is important because the farther back in time you want to look, the more the light from those early objects gets pushed out of the visible spectrum and into the infrared. So if you want to see the youngest galaxies in the cosmos, you need an infrared telescope, not an ordinary one. Webb has a huge golden mirror, 6.5 meters wide, made of 18 hexagonal segments. And that mirror gives it just enough collecting power to pick up the faintest smudges of light from galaxies more than 12 billion years old. The second telescope is the Chandra X-ray Observatory. Chandra has been up there since 1999, so it is now more than 25 years old. It was built for a very different job. Instead of looking at faint starlight, it hunts for X-rays. X-rays are produced by some of the hottest, most violent gas in the universe, gas heated to millions of degrees by shock waves, explosions, and gravity. Earth's atmosphere blocks those X-rays completely, which is why Chandra has to sit in space. It loops around Earth in an elongated orbit that, at its farthest point, carries it almost a third of the way to the Moon. Chandra does not take glossy pictures of glowing galaxies the way Hubble did. Instead, it draws a kind of heat map of the universe, lighting up the regions where supercharged gas is screaming out X-rays. Now here's the thing that makes this discovery special. Each telescope on its own only tells you half the story. Webb shows you where galaxies physically sit by detecting their starlight. Chandra shows you where superheated gas is glowing by detecting X-rays. Point them at the same exact patch of sky, and you start to see full structures that neither telescope could fully reveal on its own. To confirm something is a real gravitationally bound galaxy group, you really need both pieces of evidence, the galaxies and the surrounding hot gas. That is why this particular confirmation is so much stronger than any earlier infrared-only candidate. That is exactly what a team of astronomers did. They pointed Webb and Chandra at a single overlapping patch of sky called the Chandra Deep Field South, which happens to line up with a region already being mapped by the JWST Advanced Deep Extragalactic Survey, or JADES for short. This is one of the most intensively studied corners of the night sky. The Webb data there represents some of the deepest infrared views we have ever taken, and the Chandra data overlapping with it represents the deepest X-ray exposure the observatory has ever collected of one patch of sky. If ever there was a place for a discovery like this, this was it. When the team looked closely at this small patch of dark sky, they spotted an object they now call JADES ID1. Using Webb's infrared eyes, the researchers picked out at least 66 separate galaxies, all packed tightly together, all glowing at roughly the same distance from us. That grouping alone was already a big deal, but 66 close galaxies can sometimes still be a trick of perspective. A chance alignment of objects that just happen to sit in roughly the same line of sight from Earth, but are actually at very different distances. That is the kind of illusion redshift measurements are designed to break. That is where Chandra came in. As galaxy groups form, the surrounding gas gets dragged inward by gravity and slams together, heating up to millions of degrees in the process. Gas that hot does not sit quietly. It radiates X-rays. When Chandra turned toward that exact same patch of sky, it detected a clear X-ray glow, coming from a huge halo of hot gas surrounding those 66 galaxies. That confirmation was the missing puzzle piece. A dense cluster of young galaxies held together by gravity and bathed in superheated X-ray gas, those are exactly the two things scientists need to officially call something a protocluster, an early galaxy cluster still in the act of forming. Together, Webb and Chandra had done something neither telescope could do on its own. They had confirmed that a real, physically bound structure exists 12.7 billion light years from Earth. And that is where things start to get genuinely strange. Because of how far away the light from JADES ID1 had to travel, the astronomers calculated that they were seeing this protocluster as it existed when the universe itself was only about 1 billion years old. The technical redshift is roughly 5.68, meaning the light we just caught left its source when the cosmos was in cosmic toddlerhood. To put that in perspective, our universe today is estimated to be around 13.8 billion years old. So we're looking at a snapshot from an extremely early chapter of cosmic history, a time when the very first galaxies were supposed to still be slow cooking out of the leftover material from the Big Bang. The problem is the timing. According to the standard models of how the universe grows, a massive protocluster like this should not yet have formed at the 1 billion year mark. Most existing simulations, say big structured galaxy clusters, need somewhere between 2 and 3 billion years of cosmic history to come together. You need time for enough galaxies to be born. You need time for those galaxies to drift close enough together that gravity can actually start pulling on them. You need time for gas to fall inward and heat up enough to glow in X-rays. Every stage takes time. Roughly 2 billion years, give or take, is what the simulations predict. JD's ID1 appears to have reached the same milestone in roughly half that time, maybe even less. The scientists behind the discovery have been unusually direct about how strange the result is. Akos Bogdan, an astrophysicist at the Center for Astrophysics at Harvard and the Smithsonian, who led the study, said this might just be the most distant confirmed protocluster ever seen. He also described the early universe as, in his words, being in a huge hurry to grow up. That phrase catches the puzzle perfectly. This discovery does not break any law of physics. Gravity still behaves exactly as Newton and Einstein described. Hot gas still radiates X-rays exactly as thermodynamics predicts. What this discovery challenges is the timeline, the idea that matter in the early universe needed roughly 2 billion years to assemble a structure this massive. Let's take a moment to talk about what galaxy clusters actually are, because to really feel why this matters, you need a quick mental picture. A mature galaxy cluster is the largest gravitationally bound structure in the entire universe. The biggest ones contain anywhere from hundreds to a few thousand galaxies, all locked together, not just by gravity from their visible matter, but mostly by the gravity of enormous invisible halos of dark matter. Sitting around and between all those galaxies is a huge ocean of superheated gas so hot that electrons have been stripped away from atoms, leaving behind what physicists call plasma. In simple terms, a galaxy cluster is a glowing ocean of plasma with islands of galaxies floating through it, all held together by a scaffold of dark matter that no one has ever directly seen. Astronomers love studying these clusters because they work as natural laboratories. Because they are so massive, they bend the light coming from even more distant objects behind them. That bending effect, called gravitational lensing, acts a little like a cosmic magnifying glass that lets researchers see things that would otherwise be too faint to detect. Because they take so long to form, the size and age of a galaxy cluster tells scientists something very specific about how quickly matter has been organizing itself throughout the history of the universe. So when a fully confirmed protocluster shows up 1 billion years earlier than the models say it should, something genuinely important has just shifted on the board. Now let's talk numbers, because the size of this thing is genuinely hard to wrap your head around. Astronomers estimate that JD's ID1 has a total mass of about 20 trillion times the mass of our Sun. 20 trillion suns worth of material gathered into one forming structure. To compare that to something familiar, our home galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars, and its total mass, including its dark matter halo, is somewhere around 1 to 1.5 trillion solar masses. That means JD's ID1, which is still only a baby cluster, currently holds somewhere around 15 to 20 times the total mass of our entire Milky Way, and it built itself up to that scale while the universe was still in cosmic kindergarten. For comparison, the mature galaxy clusters we see much closer to Earth have had roughly 10 billion years to keep growing. The biggest of them contain hundreds, sometimes thousands of galaxies, all immersed in huge plasma oceans heated to millions of degrees. JD's ID1 is essentially a much younger, much earlier version of those structures, except it appears to be running at a pace that nobody expected. The fastest known protocluster of comparable size, when it was previously spotted at this kind of distance, was already pushing the limits. This one has simply gone further. If you have been paying attention to space news, this might not feel entirely new. James Webb has been turning up these kinds of surprises since it began operating. Earlier in its mission, Webb identified galaxies in the very early universe that appeared much larger, much brighter, and much more chemically mature than current models predicted. In one famous case, researchers spotted 6 enormous galaxies, dating to roughly 500 million years after the Big Bang, each one packed with tens of billions of stars. The largest looked to be about 1 trillion solar masses, around 10 times the size of the Milky Way. One of the researchers on that study famously called the result bananas, because nobody expected the early universe to be able to build structures that big, that fast. JD's ID1 fits into that same growing pattern, but with a critical twist. This time, the team had a second telescope to lock the result down. They were not just looking through infrared eyes anymore. They had X-ray eyes to confirm the gas, and that confirmation is what turns this from an interesting guess into settled science. Let me pause here for a moment, because if you have stayed with me this far, you are clearly the kind of curious mind this channel was built for. Hit that subscribe button and ring the bell so the next breakthrough like this lands right in front of you. Because the cosmos is not done surprising us, and you have already proven you can keep up. Let me come back to the patch of sky where this was found, because that is part of what makes the story even more interesting. The area being surveyed here is the JD's field in the southern sky. In an earlier study, a different team led by Chong Lee and Professor Christopher Concelis at the University of Manchester had already identified 6 protocluster candidates in the same patch of sky using Webb's infrared data alone. So there are 6 strong suspects sitting in this single field. But out of those 6, JD's ID1 was the only one where Chandra was able to detect the signature of hot gas. The other 5 candidates are still just that, candidates. They might be real protoclusters too, but without a confirmed X-ray halo, scientists cannot be sure they are genuine gravitationally bound structures rather than just clusters of galaxies that happen to overlap from our view here on Earth. This is the only one of the bunch that has been formally confirmed and published, and it appeared in the journal Nature on January 28, 2026. The way the team actually nailed this down took painstaking work. First, they had to identify each of the 66 galaxy candidates inside the Webb infrared images, and then measure the redshift of every single one. Redshift is how astronomers figure out how far away something is by measuring how much its light has stretched during its long journey through expanding space. Only after confirming that all 66 galaxies had similar redshifts could the team say with any confidence that they were actually at the same distance from us, rather than just appearing close together by coincidence. Then they had to dig into the Chandra data, filtering out background noise and unrelated X-ray sources, and isolate the faint X-ray glow coming specifically from that pocket of sky. That required combining some of the deepest, longest X-ray observations Chandra has ever taken of one patch of sky. None of this was easy. Both telescopes were working right at the very edge of what they could possibly detect. Christopher Concelis, one of the co-authors of the new study, put it simply. He explained that discoveries like this happen only when 2 powerful telescopes stare at the exact same patch of sky, right at the technical limit of what each instrument can see. That is not dramatic wording. That is just true. Webb had to detect 66 extremely faint smudges of infrared light, each one a baby galaxy whose light had traveled for over 12 billion years before reaching us. Chandra had to pick up an X-ray signature so faint it required years of cumulative exposure on the same field. Both telescopes had to be perfect. Both had to be patient. And even with all of that, the discovery came right down to the wire. So how did we get a structure like this so early? Right now, scientists are weighing a few possibilities, and they are all genuine options. The first possibility is that galaxy formation in the early universe was simply faster than the simulations assume. Maybe the very first generation of stars used their gas more efficiently than current models expect, turning raw material into galaxies at a more rapid rate. Maybe star formation was more violent back then, with massive short-lived stars pumping out energy much faster than the slower stars that dominate today. If that is the case, then the universe may have been producing galaxies at full speed from very early on, and our existing timelines simply kept undercounting. The second possibility is that dark matter itself clumped into large-scale scaffolds much earlier than expected. Dark matter is the invisible material that shapes where galaxies can form by providing the gravitational wells they fall into. If dark matter clumped earlier and more aggressively than simulations currently predict, then the gravitational scaffolding needed to pull galaxies into a tight protocluster would have already been in place, ready to gather everything up. The galaxies would not have needed to wait. The trap was already set. The third possibility is that this particular region of the early universe was simply an unusually dense pocket of matter, a rare statistical outlier rather than a sign that this kind of rapid cluster formation was happening everywhere. There is a real difference between one weird spot and a universe-wide shift. With only one confirmed example so far, scientists cannot tell yet which scenario is right. It could be all 3 in different regions of the sky. A fourth possibility, less talked about but worth mentioning, is that the standard cosmological model itself might be slightly off in ways we have not yet identified. Maybe the mix of dark matter and dark energy in the early universe behaved a little differently than present-day observations suggest. Maybe our measurements of how fast the universe is expanding, known as the Hubble tension, are pointing at something deeper. None of that requires rewriting physics from scratch, But it could mean the small tweaks inside the model need to be bigger than anyone has been comfortable proposing until now. And that open question is exactly why this discovery matters so much. It is a real anomaly, a real data point that does not fit neatly into existing theory. Anomalies like this have always been how science moves forward. They force researchers to refine, and sometimes completely rebuild, the models we use to describe how the universe evolved from a smooth, hot soup into the vast, complex web of clusters and superclusters that fills the sky around us today. Let me zoom out for a moment and put this in even bigger context. Right after the Big Bang, the universe was almost perfectly smooth. Tiny density differences, smaller than 1 part in 100,000, were already baked in. Over time, gravity pulled those slightly denser regions together. They grew into filaments and walls of dark matter with emptier regions between them. Galaxies formed along those filaments, and galaxy clusters formed where multiple filaments crossed, the cosmic intersections of the universe. The Standard Model has a timeline for every stage of this process. It says the very first small dark matter halos collapse within the first few 100 million years. The first stars turn on, ending the Dark Ages. The first galaxies begin to take shape somewhere around the half-billion-year mark after the Big Bang. And only after that, slowly, do clusters of galaxies start to bind together. That is the established picture. JD's ID1 is now sitting on top of that picture, saying, softly but clearly, that the timeline may need to be rewritten. It is worth pausing to appreciate how rare this kind of finding actually is. To be confirmed, JD's ID1 needed Webb to count 66 galaxies, Chandra to light up the surrounding gas, redshift measurements to put them all in the same place and time, and computational models to estimate the total mass. Each of those steps could have failed. The galaxies could have been spread across multiple distances. The X-rays could have been too faint. The mass estimate could have been too uncertain to publish. Instead, every test lined up. That is why this made it into Nature, one of the most selective journals in science, rather than into a press release with thin evidence. The bar for this kind of announcement is high, and the result cleared it. A quick favor before we move on. If this breakdown is hitting the way I hoped, drop a like, leave a comment with the single moment that hit you hardest, and share this with one friend who still thinks astronomy moves slowly. They are about to find out how wrong that impression has become. Now, none of this means the discovery is breaking physics. It is not evidence of anything artificial, and it is not physically impossible in any sense that violates the actual laws of physics as we currently understand them. Gravity still pulls matter together exactly as Newton and Einstein described. Hot gas still radiates X-rays exactly as thermodynamics predicts, the same physics that applies when water boils on a stove, just scaled up to cosmic temperatures. What is genuinely surprising is the timeline, nothing more. That distinction matters because it is the difference between a mystery that genuinely expands our knowledge through careful evidence-based science and a sensational claim that is not supported by the actual data. The carefulness of the work behind JADE's ID1 makes that point clearly. It is real science, not hype. Looking forward, the plan is clear. Astronomers want more objects like JADE's ID1. They want to keep pointing both Webb and Chandra at overlapping patches of sky, and they want to turn future observing time towards specifically hunting for more protocluster candidates in the first billion years of cosmic history. A single confirmed example, no matter how stunning, is not enough to fully rewrite the standard model of how galaxy clusters form. But if more objects like this start showing up, scattered across different parts of the sky, that would strongly suggest the early universe really was building big structures faster than current theory predicts, and the model would need to change. Future telescopes will help. The Nancy Grace Roman Space Telescope is being prepared to launch in the coming years, and it will do wide-field infrared surveys that can scan huge stretches of the sky for exactly these kinds of overdensities. Euclid, launched by the European Space Agency in 2023, is already doing similar work with a slightly different focus on weak gravitational lensing across the universe. The Atacama Large Millimeter Array, often called ALMA, can also catch early dust-enshrouded galaxies that even Webb might miss. And the James Webb Telescope itself still has years of fuel left and a long list of approved deep field programs waiting their turn. Between all of those instruments, the next decade of cosmological observation is going to be one of the most consequential ever, and JD's ID1 is essentially the opening example. At the same time, if JD's ID1 turns out to be a rare exception, an unusually dense pocket of an otherwise ordinary early universe that would still teach astronomers a great deal. It would tell them about how much unevenness existed in the early cosmos, and about how dramatically matter could vary from one region to another in those first chapters. It would also give them a real-world benchmark for how fast matter can collapse in extreme conditions, which feeds directly into models of galaxy formation everywhere. Either way, the message from this discovery is the same. Even with tools as advanced as the James Webb Space Telescope and the Chandra X-ray Observatory, both of them pushed to the very edge of what they can detect. The universe still has surprises tucked inside its earliest chapters. It is just waiting for the right instruments to look in the right place at the right time and notice what is actually there. One last thing before we wrap this one up. If you want more fact-checked breakdowns of discoveries like this one, hit subscribe and share this video with someone who still believes we have already mapped most of the early universe. They need to see this. Drop a comment below telling me what surprised you most. The 20 trillion solar mass figure, the fact that this structure formed 1 billion to 2 billion years earlier than expected, the 5 other unconfirmed protocluster candidates sitting in the same patch of sky, or the fact that 2 telescopes had to work together at the absolute limits of their capabilities just to confirm that one real object existed 12 billion light years from Earth. I genuinely want to know what caught your attention. Thanks so much for staying with me until the very end. I will see you in the next one.